Okay, thank you. So, thanks for the introduction. So today I'd like to talk to you about some work that we've been doing, and in particular, a problem that we have elicited from about a decade of work with the industry. And in particular, we've been working with an industry that is, or industrial partners that are interested in deploying fleets of autonomous robots in industrial settings. These settings vary quite widely from warehouses to, for example, quarries where autonomous haulers are supposed to displace rocks, to drilling machines in mines, open pit mines, and kitting robots, feeding production lines. In all of these applications, you can imagine there are a variety of open planning problems and scheduling problems that have to be addressed in conjunction with the fact that these are fleets of autonomous robots that are carrying out the tasks. But today I'm not going to focus on what distinguishes these application scenarios, but rather what makes them all similar to some extent. So in all of these situations, we're interested in doing what I'm showing you here in a very simplified scenario. We'd like to be able to command this fleet to reach certain destinations. So we'd like to be able to post goals to robots in the fleet individually, online, on the fly, and we would like these robots to plan motions according to their own kinodynamic models to reach these poses, and in doing so we'd like them to coordinate while navigating in this common space. Okay? So in essence what we're interested in here is in the minimum common denominator that there is between all these application scenarios. We're interested in finding automated solutions to the motion planning problem, that is the problem of finding paths for robots with non-trivial kinodynamics, the control problem, the problem of synthesizing control actions that brings about the execution of these trajectories, and of course, last but not least, the coordination problem. That is the problem of regulating movements of these robots in a shared space. And as said, this problem is elicited from a decade of work with different industries and different application contexts where we have different robots, each with their own specific kinodynamics perhaps, controllers, and so on. So we cannot impose the use of a particular solution for motion planning. We cannot make strong assumptions on what our robot controllers can do. They often come as black boxes that are built into the platform. And we cannot assume a homogeneous fleet of robots either. And in addition, we have to remain open to the task level reasoning that we do on top of this fleet. So we need to be able to post goals online, as I showed you in that simple example, and to do this for an arbitrary subset of robots at any point in time. So in this paper, we propose what we like to call a controller for a fleet of robots. And this controller has the characteristics that I showed you in the previous slide, namely, you can post goals online, robots can be varied with different geometries, kinematics, and dynamics. We will make very few assumptions on robot controllers and on motion planning. Importantly, we will not need to discretize in any particular way the environment or the motions of robots, and we can inform the control method via heuristics that account for robot dynamics. Okay, now there's obviously lots of existing work here in the field, for instance, of multi-agent pathfinding, multi-robot pathfinding, planning for multiple robots in coordination space, multi-robot control. There are good reasons why many of these or all of these approaches have or don't satisfy all of our requirements. These are in the paper, which you can then see offline. So let me jump directly or cut directly to the chase. Here, let's establish some vocabulary. We're assuming that path planning is the problem of finding or determining a path that leads a robot from a start configuration to a goal configuration in some configuration space. We are assuming also that there is a control problem, namely that is the problem of determining a temporal history or a temporal profile that in combination with this path leads to a trajectory that is executable, subject to perhaps differential constraints. Okay, so this is what we assume path planning and coordination are. And of course now, well, we get to the core of it, reasoning about how robots collocate in space. For that purpose, and for the purpose of defining the coordination problem, we start by defining what a spatial envelope is. A spatial envelope is a set of robot transformations that can be reached along a path of a robot. Now this is a particularly simple example of spatial envelopes here. They are very simply the sweep of the robot geometry along these reference paths, but it could be something more general. I'll say a few words on that later. Now if we can do that, we can define what we call a critical section, and that is a maximal contiguous intersection of spatial envelopes. Okay? So this area here would be a critical section, and in fact, let's look at this other critical section. You can see that there are another two interesting attributes of a critical section, namely the infimum and the supremum of a critical section, and that is the poses at which a robot's geometry begins to intersect with a critical section and the pose at which this state of affairs ceases to be the case. So you could see these as the entry point to a critical section and the exit from this critical section. So if we can do that, then we can define precedence constraints. Precedence constraints being, quite simply, constructs that regulate access, concurrent access to the critical, to a critical section. In particular, a precedence constraint, as we defined it in the paper, is something that is purposefully simple. It is a representation that tells us that robot I, navigating along path PI, may not navigate beyond configuration QI until robot J, navigating along path PJ, has reached configuration QJ. So like in this particular case, this gray arrow represents this precedence constraint, which regulates the access of R2 and R3 to this critical section, stating that robot 2 may not navigate beyond Q2, which is the infimum of the critical section, until robot 3 has reached Q3, which is the supremum of the critical section. Okay? So it's important to note that precedence constraints essentially prescribe a critical point. A critical point is a point beyond which a robot may not navigate. So we can reduce now, or we can define now, the coordination problem as that of finding a precedence constraint for every critical section. Okay. Now, critical sections or constraints, let's say, as I've defined them earlier, they should be seen as impositions on the temporal profiles of the trajectories of robots through the spatial envelopes. And regulating or deciding these constraints should lead to something like I just showed you here. The robots, if robots adhere to the constraints, if robot controllers adhere to these constraints, then the robots will not collide. It's important to note before I show you how this is done that we need to accept situations like this one, where a fleet that is in motion, where robots 1 and 2 are already in motion, all of a sudden gets confronted with the fact that robot 3 now needs to navigate to a new location. And a motion for this robot is computed on the fly and coordinated together with the motions of other robots. So this is what we're aiming for. And the way we realize this is by, as I anticipated, realizing a control loop for the fleet. So this means a set of reasoning steps that occur over a period t, which can be in the order of half a second or tens or hundreds of milliseconds. And it's actually really quite simple. What happens is that we, like any classical control scheme, we would sample the state of robots. For each robot that is idle and for which a goal has been posted, we can compute the spatial envelope that reaches the posted goal. Note here, I'm not really making any assumption on how this computation happens. I'm just assuming there is some kind of motion planning capability or algorithm that computes a spatial envelope to reach the goal. Once that is done, we can update the set of critical sections. This reduces to finding intersections of spatial envelopes. And once those are found, we can compute resolving precedence constraints, because again, as we said before, we must have or we're looking to calculate a critical point that regulates access to every critical section. Now, once these constraints are revised and computed, all we need to do is to communicate them to the robot controllers. And here another point that is worth emphasizing is that what we are communicating to robot controllers are critical points. We're not communicating some complex instruction. We're just giving them a set point beyond which they are not allowed, or the robots are not allowed, to proceed along the reference path. So a first simple way in which we can bring about this kind of coordination is to compute the precedence constraints as follows. So as you see in this example, we can see these critical sections. There are 3 of them here, 1 for every pair of robots. We can see these critical sections as binary resources, right? So we could compute constraints that impose the exclusive use of a critical section by one robot. And this is very easily done by simply saying that the critical point is the infimum of the critical section. So every robot will be forced to wait at the entrance of the critical section until the robot that precedes it, or that is given precedence, has exited it. Now, of course, this guarantees that trajectories do not intersect. However, or that the trajectories will not collide. However, it is very inefficient if the motion is in the same direction, clearly. So, whereas that would be perfectly acceptable in a situation like the one on the bottom left, where the robots are progressing in opposite direction or in opposing directions, we would actually like robots to be able to follow each other through a critical section in a situation where they're traversing in the same direction. So that is essentially why we define this critical point as a function of time. In the paper there are details, but essentially you could probably imagine that it's quite simple to computate. There's not much computational overhead in finding the point up to which within a critical section a robot can proceed before it collides with the robot that is preceding it. And therefore, as said, this constraint now becomes something that imposes an ordering, but also a critical point that is a function of time and can be updated. Again, why can we update it? We can update it because this is a control loop, because we sample the state of robots at every period. So what remains to be answered is how do we compute the precedences? How do we decide who goes first, essentially, critical sections? Well, of course, we'd like to be informed by a heuristic. There is obviously a naive choice that's possible, and that is that you could make an idle robot always give way to robots in motion, but that would obviously be naive. We want to be informed by a heuristic, but in order to do that, we need to make sure that an ordering is imposable. And an ordering among robots in motion is imposable only if it is dynamically feasible. That is to say, the robot that must yield is actually capable of stopping. How do we do that? Well, for that, it's relatively easy to see that we could use a forward model and compute whether or not a particular ordering can be imposed on the fly. This is not difficult if you use a simple but conservative forward model of the robot dynamics. In the paper we show an example where we use a constant acceleration-deceleration forward model, and how this can be used to define the set of at most 2 possible orderings in every critical section that constitutes possible orderings. And if we can do that, it's quite easy to prove that no matter what heuristic you substitute into the algorithm, you will be able to obtain a safe state, or your machines will actually be able to, or the orderings that are decided on the fly are dynamically feasible. So in the paper we have some evaluation. We've evaluated our approach for scalability. We can scale to tens or about 50 robots when everything, the robot simulations and the algorithm, are running on one machine. Here's an example where we emphasize something else, and that is the fact that these robots that are random, or that are for which a random goal is posted, or sorry, a goal is posted every time they reach a destination to reach the opposite end of the environment, and a path is computed on the fly with an RRT-based motion planner. What we're emphasizing here is that we really don't care how robots get to critical points. Robot dynamics are only considered insofar as we want to evaluate whether a particular ordering is feasible. But actually how robots drive before a critical point, in reaching a critical point, is none of the coordinator's business from that point of view. So we really don't make too many assumptions on the robot controllers, only that they will stay within the spatial envelope and they will not go beyond a critical point if such a point is communicated. This is to say that our approach doesn't just work in simulation, it's integrated with real robots. Here are 2 robots running around in our basement, coordinating in moments of when they traverse areas that are tight and that don't afford parallel motion. Here again the motions of the robots are computed on the fly, and they are in fact here computed with a lattice-based motion planner, whereas in the previous example I told you about, they are computed with this RRT-based motion planner. It's worth emphasizing just one more thing. Here's a detail of what goes on in that tight corridor. The fact that we are revising the choice of precedence over in critical sections in this sort of online scheduling-like way, informed by a heuristic, is what allows this robot to overtake a robot that is in which we have provoked an error state on purpose. So this continuous revision of who goes first is important. Now, I think that is one of the key points of this work. If you're interested in using this library that we've implemented, it's available on GitHub. A Java implementation is provided. It provides generic interfaces towards robot system and the motion planning system that you choose to use, in addition to providing a built-in simulator and motion planners. There is also a provision of interfaces towards ROS and other robot systems. So, in summary, we've presented an integrated motion planning, coordination, and control approach. We've realized a loosely coupled approach which provides essentially a robot fleet controller. The fleet can be heterogeneous. The goals can be posted online. It can be used with off-the-shelf motion planners and control modules, making very little assumptions on them. And it employs user-definable heuristics and dynamic models. And with that, thank you, and I'm open for questions.
Thanks, Federico. Any question? Yes, it's easy.
I've actually a couple. The first one, does the method...
Speak in X.
Okay, interesting. I have 2 questions.
Yes.
By the way, very nice work. The first one is, does the method allow to have, in case of interaction between 2 robots, a completely different path for one of the 2? I'm referring to robots that are, for example, moving on rails, where basically for going from my point to your point, and then you need to come to my point, actually you need to move further away before you can give, in order to give priority to me, and then you can move back in.
So the question is whether the paths can be, well, the paths are computed on the fly by whatever motion planning strategy you choose to adopt.
Yeah, but the paths are computed also
with reference,
considering all the path of all the other robots.
I see,
yes.
I see your point. So this is a very interesting question. You could do that. What's notable in this approach is that you don't have to. So the robot paths are computed individually. This obviously keeps down the complexity of the control loop, of every iteration of the control loop. That's the fact that we're not by default doing multi-robot motion planning, which for example in a systematic approach would double the branching factor if you have 2 robots, so it becomes a nightmare, is an advantage. However, you may want to do that, for example, to avoid deadlocks. Deadlocks in fact are an open issue, but they can be avoided exactly by doing what you say, and that is considering the motions of 2 robots together when you're trying to compute them. So this is possible. There's a technique called prioritized motion planning, which I've mentioned here somewhere. Right. Prioritized motion planning could be used to do that. And hope that answers your question.
Okay. I'll probably bother you more afterwards. The second question, can you give us some further information regarding the spatial envelope? Does it, for example, consider spatial envelopes that are not convex, or they are completely separated? Basically, the footprint of the robot is not a convex
That's
footprint.
a cool idea. So the spatial envelope need not be convex. It is not convex in these cases. The footprint of the robot, the robots that we've looked at so far, are typically convex. I can imagine a robot that's sort of, I don't know, maybe something that has...
A crane.
A what?
A crane, for example.
A crane. Okay.
But actually the legs are two separate.
Yeah, yeah. I don't see an issue. I'm not entirely, because basically the computational geometry behind this is rather simple. It's simply finding intersections of spatial envelopes, and if the intersection of two spatial envelopes is what says that there is a possible collision, then you're good, no matter what the geometry is.
Thanks.
Other question? Yeah.
So it's very interesting work, and did you observe any interesting behavior? Because always when you have optimization and this global planning, did you observe some, I don't know, behaviors of your robots which are not known in before? So.
That's a nice question. Let me show you a video. Maybe, I hope this answers your question, or maybe it starts to. So these are 17 robots that are going towards charging stations. And this is a real scenario in a quarry, and these are Volvo machines, autonomous Volvo machines, not cars, but haulers. And the interesting thing is that the person we were working with told us, well, in this scenario, in order for the whole scenario to work, I won't get into the details, you'll need 8 machines. And we said, well, I'm sure that I thought more machines I throw at the problem, then the better the throughput of this mining operation. And in fact, it's not the case. The guy was actually right. This is a total waste of time because, as you see, there's significant amount of queuing up here because the machines have to charge, because they do non-trivial operations when they reach places, and that takes time. Maybe in partial answer to your question is that you could do what-if analysis in a pretty simple way with this approach, and what I've seen personally is that when domain experts tell you that something's the case, it usually is.
Okay. I guess it's time to go for the coffee break, so I would thank again Federico